All right, here we go. Part 3. We'll continue on with our numerical stuff. Values we have described are values for a specific color. Color difference numbers are what we're really interested in. So each color has a unique set of values for L star, A, B, C, and H. So that represents a certain color. But in color matching, the absolute numbers, which is what we're kind of talking about here, aren't the most important thing. What we're more interested in is the delta numbers, or the color difference numbers. We have a color that we're trying to match. It has a set of absolute numbers. We make a batch up, try to match it. It has a set of numbers that go along with it. What we're really interested in, what's the difference between those two sets of numbers? Those are what's called the delta numbers. The C-Lab color difference numbers that are used in industry are difference in the individual values for the standard, which is the color you're trying to match, and the batch, the sample you made up to match that standard. They're denoted by either a capital D, a small d, or a triangle in front of the value. So delta A can be expressed in any one of those three different ways there. They all mean the same thing. So this is the actual equation. And these are the equations you'll be doing. These are pretty simple. You ought to be able to subtract two numbers from each other, even without a calculator. I know that may be pushing it. Some of us used to actually learn how to do that before you used calculator. To get our calculations for LA and B, or delta LA and B, we just take the value for the batch and subtract the value for the standard from it. And that's really the important thing. It's always the batch minus the standard. It's important to get the sign right. So here's just some more of those equations. L, C, and H this way. When we start getting into C, that's a little bit more complicated because we have to start with A and B to calculate C for the batch. What this equation here means is we take the A value, square it, plus the B value, square it, then you add those two things together, and this little half value there means the square root. It's just you can't make a square root very easily with computer or word processors. That's all that means. That raised to the half power is the same as the square root. You get a value for the C of the batch, and then a value for the C of the standard, and then you just subtract them. Here, delta H, we can't calculate directly. Like the delta L, we can calculate from the L of the batch and the L of the standard. Same thing with delta C. But delta H, there's no two H values for each one, the standard and the batch, that you can subtract. So the way you have to do it is you take the total difference, which is delta E, square that, subtract the delta L value that's squared, and then subtract away the delta C value, and then whatever is left is the delta H. So if you think of it, you have your total, subtract out the delta L, subtract the delta C, and you get the delta H. So you have your total difference, take out whatever the difference is due to the lightness, take out whatever the difference is due to the chroma, what you have left is the hue, because it's got to all add up to the total. So that's how you do the actual calculation. When you think about it, there's two different ways of calculating delta E. You can do it this way. You take the delta L, square it, plus the delta A, square it, plus the delta B, and square that, add all that up, and then you take the square root of it. This is the type of equation that is used for finding the difference between 2 points in a three-dimensional space. That's where that comes from. It's just that our three dimensions have to be lightness, red, green, and blue, yellow. But any coordinate system that had three dimensions, you would calculate the difference between it. One of the reasons you square these is that these could be, this delta L, A or B, could be positive or it could be negative. So if you didn't square them, you could subtract it out. There's no subtracting going in here. So whatever these values end up being when you square them, they're all going to be positive. Then you take the square root of it and you get the value. Another way of calculating delta E then is L, C, and H. In either case, for a given pair of samples, because these numbers represent two different samples, is these delta E values are the same for that given pair. You just break it down into two different ways or two different sets of categories for the difference. We can describe qualitative differences. Not only are values of the differences important to describe the magnitude of the difference, that would be quantitative. Sign, positive or negative, denotes the direction of the difference. That's what we mean by qualitative. Is it too red or is it too blue or whatever? We can tell by looking at these numbers. Delta L is our lightness, darkness difference, or we can say the shade of gray or even the white-black difference. If the sample is lighter than the standard, it'll be a positive number. If the sample is darker, it'll be a negative number. Even without looking at the samples, we can get these qualitative differences. The red-green color difference, the delta A, if the sample is redder, it'll be positive, and if the sample is negative, it will be greener. Or we can use the opposite terms. You can see either redder or less green. That technically means the same thing. Or greener means less red. Again, technically means the same thing. But just think of why you would use one value versus the other. Let's say you had an orange that you're trying to match. You had a negative value for the difference. So if you had an orange, would it make much sense to say this orange is greener than this other orange? No, it wouldn't really make any sense. You would say one orange is less red than the other one. If we were dealing with a greenish yellow, we would use the term greener or less green. Even though you could use the other opposites and technically be right, it doesn't make much sense when we talk about colors. The last axis there, the blue-yellow color difference axis, the delta B, if the sample is yellower or less blue, however you want to say it, we'd get a positive difference. We'd get a negative difference if the sample is bluer or less yellow than the standard we're trying to match. Delta C, or the chroma difference, is the difference in chroma or saturation or purity, however you want to say it, of the color. If it's positive, it's more chromatic. If it's negative, it's less chromatic. Or if we think of it in terms of where on the diagram it falls, it's farther away from the center of the diagram. Delta H has to do with hue, difference due to hue only. And positive, negative really doesn't have as much meaning there. It's just different hue. Positive would be if you're red up towards the yellow. Negative would be down towards the blue. But it just means a different hue. With all of these numbers, or all of these values, the bigger the numerical value is, the farther off it is. And then delta E is our total color difference, and it takes into account the difference in all directions. In terms of mathematical space, the total difference from one point to the other point, irregardless of what direction it goes in. Kind of remember that, because that's one of the problems with our numerical system, is all the differences, no matter which direction it's in, are mathematically accounted for the same. When we look at colors, that's not the case. Some differences we can see easier than other differences. And as we go through, we'll explain that more. We can show those differences in terms of a graphical representation. Remember, numbers can be looked at or described as numbers, but we can also use tables. We can also use graphs, plots. We call this a color plot, actually. It can show those numbers graphically, and sometimes when we show values graphically, we can understand what it means a little bit better. Let's look here. We have two colors, A and B there. They're in this direction. There's a positive yellow and a positive red. Positive A and positive B means it's an orange. So we can look at these two values. The distance here, delta A, we could actually measure it. We knew the scale here. That's the difference in the A direction, and the difference in the B direction is the delta B there. We're assuming, since they're on the same plane, that the L value is 0. So the L difference is 0. If we're saying, let's just say that the standard is A, how would we describe the trial, which is B, in terms of words, red, blue, green, yellow, difference are they? How is B different than A in terms of the red-green scale? Would the A be positive or would the A be negative? The delta A. I think it would be positive or negative. Be positive because it's, if we drew a line straight here, it's to the right or the positive side of this sample, so it would be positive. For up here, what would we say in the B direction? It's below it, so it's negative. So we would say then that B is bluer than the sample, or actually since it's up here, we would say B is less yellow than A, and we would say B is more red than A. Delta A would be positive, delta B would be negative. So that's how we can get those values from looking at a graph versus looking at the numbers themselves. Because when we look at our computer printouts, we can look at it in terms of a table of numbers that gives the delta L, A and B and C and H, or we can get a plot that shows points on a curve like something like this. It's a little different, but it gives this same sort of information. Hue and chroma differences we can look at this way. These are the same chroma calculations as we saw earlier. And if we want to measure the delta H value, you can see it's that dashed line there, and the differences in the C is difference from this point to this dashed line here would be the difference in the C value. Just to give you another way of looking at the differences there. We usually don't use the hue angle very much in industry. We'll use delta H, delta capital H, which is the hue difference. We don't use hue angle very much, but you can if you want to. Here's just a picture, the delta E difference kind of graphically, and there's our equation again on the bottom, and it just shows our sample and our standard and the different components of the total difference. It takes into account the B difference, the delta B, the A difference, the delta A, and also the L difference, delta L. Puts all that stuff together and calculates out our delta E. When we do our calculations, this is how we do it specifically. We have an L, A, and B absolute values for our sample. We have our L, A, and B absolute values for our standard. We subtract the standard from the sample, and we get our delta numbers there. In this example, we take for L 71.9 minus 69.7. We get a positive 2.2. A is positive 10.2 minus a positive 12.7. We get a negative 2.5. And then B is a positive 58.1 minus a positive 60.5. And we get a delta B of negative 2.4. That's how we calculate. For the results, the sign describes which direction the color is different. The number describes magnitude. So in that example, our positive 2.2 means the sample is 2.2 units lighter than the standard because it's positive, so it's lighter. Delta A is negative 2.5, so that means that sample is 2.5 units greener than standard because it's a negative value. The delta B is negative 2.4, so it means the sample is 2.4 units bluer than the standard because it's a negative value. That's what we can get from those numbers. Those numbers are all kind of close together, 2.2 to 2.5. So that would mean that they're all about distance apart visually. The value that's too much light, or it's too much greener, or too much bluer, all about the same amount. Now, what does 2.5 units mean? It's hard to describe what the units mean. Just keep in mind that bigger means farther off, lower means closer together. So always sample minus the standard, and we've gone through these things before, what the positive and negative values are for the L, A, and B, or the delta L, A, and B, because that's what we're talking about, the difference. Now, here's a school bus. As you can easily see, that school bus is yellow, bright school bus yellow. And what we have here are for that color, for the LAB numbers for the Hunter Lab system and the LAB numbers for the C-Lab system. And you can see they're different. not too far off in L and in the A, but the B values are quite a bit. Subtract one from the other in this case. Previous slide is supposed to be of a yellow, bright yellow school bus. That is what the numbers represent. Use your imagination. Since we have those two sets of numbers, if we want to get some meaning out of them, we need to make sure of several things. LAB numbers have no meaning unless you specify whether you're using the Hunter Lab or the C-Lab system. You got to know that to be able to do the right calculations. You also need to know what's the illuminant. Remember, that's part of the calculation. You need to know what the observer is. Remember what the two kinds of observers are? What are the two possible observers? It's not the 045, no. It's either you're looking at a little sample or a big sample, or 2-degree or 10-degree observers. And that's the field of vision you're looking at. And then, or the instrument geometry, which would be sphere and the 045. Remember, if you say 045 or 450, that's really the same thing. The two types are the 045. Remember, that's really how our eyes look at it, or the sphere, which collects all the spectral energy. If you have one versus the other, you're not going to be able to compare those two sets of numbers. So you need to know these things before you know exactly what you're talking about. And that's why I said it's so important for there to be a operator that knows what they're doing, because if they don't, you can get wildly different numbers and they think they're comparing the same thing, when in fact they're not. Because if these aren't all the same, there's no way of comparing those numbers. Scale, Hunter Lab or C-Lab. As you can see from the picture of the school bus, those numbers are not the same for both scales, especially the V values. They were like 30 points different, 30 numbers off. Illuminant, remember from model for color that the illuminant is part of the calculation, so it must be specified and the same for the numbers to be comparable. So you either have to have D65 or illuminant A or cool white fluorescent. You know, it can't be two different fluorescents. It can't be D65 versus D75. Those are all different. 2-degree or 10-degree observer. I mentioned functions are different, resulting in a different number describing the color. And the instrument geometry, the 045 geometry, will result in different values than the spherical geometry. It shows the difference in the values. Again, when we talked about this, the lightest one of these, which would be the highest positive number, would be the sphere, which is the D/8 spectral component included, because we're collecting all of that specular energy. If you notice the C and the H, they're not that much difference, but the L is the biggest difference. Next lightest would be the sphere, D/8 spectral component excluded, which would be 47.5. And then the darkest would be the 045, because all of that specular reflection is lost. And if we look at these values for differences, 4.7 and 8.3, those are big differences. In general, and this is a very general statement that doesn't always hold true, but in general, if your delta E is greater than 1, good chance it doesn't match. If it's less than 1, good chance it does match. You can see those values are much greater than 1. The C-Lab plot can describe information about the relationship in color of a group of samples. The next few slides will discuss how. The plot on the next slide shows where in C-Lab color space 7 points, A through G, our individual samples are located. The letters A through G represent actual color samples, and we're going to plot them in color space. For this example, we're assuming all the L values are the same. Delta L for all of these values is 0. We have 7 colors here, okay? And we see they're all over color space. This is our center point here, so this is basically whites, blacks, and grays right there. The farther out we get from it, the more chromatic it can be. How are these values the same, and how are they different, and how can we tell that by looking at this particular plot? Well, we can, by looking at the plot, determine which values have the same A value. Any points that fall on the same vertical means up and down, line have the same A value. So if we look at our graph again, samples A, B, and C, and F have the same A value. If we draw a line there, why it's good to use graph paper on this. We see that A, B, C, and F all have the same absolute A value, which in this case from our graph is 4. So they all have a value of 4. Because remember, that's how we plot it. If we want to plot A, or we want to know what numbers A has, it has an absolute value of A of 4 and a value for B of 6. So that's how we apply it. B, C, and F all have a value for A of 4. They have different B values. B is a positive 4, C is a positive 2, and F is a negative 4, but they all have the same positive A value. That's how we can tell that from the graph. By looking at the plot, we can determine which values have the same B values. Any points that fall on the same horizontal or sidewise line have the same B value. Samples A and D and samples B and G have the same B value, but the two sets are different. So now this shows the values with the same B value. B and G both have a B value of positive 4, and A and D are the same, and they both have a B value of positive 6. So by looking at the plot, you can also tell that. H and F are different. One is a negative 3, one of them is a negative 4. Looking at the plot, we can determine which values have the same hue. Any points that fall on the same line originating from the center of the plot, which is 0.00, and radiating out. So samples B and D have the same hue. Note sample H is not the same hue as B and D because it's on the other side of the graph. This shows that. If we draw a line from the center point through sample B and continue on, it goes through sample D. So any point on that straight line would represent a color that has the same hue. It would have different chroma values, but it would have the same hue value. As I mentioned in that previous slide, we could draw the line back this way, and it would go through color H, but that's not the same hue because these two would be orange. B and D would be an orange. Sample H would be a blue-green. And hopefully, by now, that you understand that an orange is not the same hue as a blue-green. Then we can also determine which values have the same chroma. So any points that are the same distance from the center of the plot, again 0.00, or any points that fall on a circle that is centered on that point. So if we drew a circle around the center point, any point on that circle is the same chroma. Samples B, F, and G are the same chroma. I didn't draw a circle, but if you measure this distance from the center to F, the center to B, and the center to G, that's all the same distance. So if that's the same distance, we have the same chroma. Again, that's how you can do that from the plots. You could do that also from knowing the individual numbers and doing the calculations, but you can do it with a plot too. So either way, you can do it.